This video reviews the Flexure test calculations for the AASHTO test T97, which is third point loading of a Flexure beam. Let's zoom in a little bit, take a look at our calculations and see what we can glean from the data that we've collected. You should have hopefully found the worksheet for Flexure testing and entered the data that we had mentioned at the end of the previous video. Our span length, in addition to what you previously saw, our span length will be 18.00. The peak load, which we mentioned previously, was 9,750 pounds. We had 3 width measurements and 3 depth measurements. The width measurements were 6.03, 5.99, and 6.00. So we want to calculate an average of those. So we'll sum those up to 18.02, divide it by 3 because of the 3 readings that we had, will give us a total of 18.02 divided by 3, which is an average width of 6.01. The 3 depth readings we were given was 6.09, 6.03, 6.06 for a total sum of 18.10 inches. That sum would be divided by 3 to calculate the average, and that would give us an average of 6.03. For those of you using 4-function calculators, be careful when you're adding to get that sum. You need to hit the equals button after tallying the 3 numbers so that you get that total of 18.10 or 18.02 as it was previously mentioned regarding the width. And then once you have that total, then divide by 3. If you don't tally it to get the total, your calculator will just divide 3 into the last number and you'll get an average width or depth that looks really funny. So once you have that information in hand, the average width and the average depth, the next step is to calculate the modulus of rupture. So we call it a flexure test, but really the actual strength is called the modulus of rupture. It's to be averaged to the 5 psi. Oh, and a footnote on the 5/100ths that we're supposed to measure the width and depth to, that would be at least 5/100ths. If you have a calipers that measures to the 100th, please use as accurate a number as you possibly can. So sliding up here, taking a look at our calculation for the modulus of rupture, you may recall from our previous video that the fracture was in the middle third of the span. So as a result, we used the case 1 calculation equation, which is PL over BD squared. P is the peak load, L the span length, B the width, and D the depth. So we multiply the load times the span length, divide it by the width, and then divide it by the square of the depth. Now on this, you can either square it in advance, or you can go divided by 6.03, divided by 6.03. Doing that twice will also get you the calculation. And some have found it useful to multiply the top 2 numbers, write down what that number is, multiply the width and depth squared down to the bottom, write what that number is, and then manually divide the 2 together to get the final total. In this case, that total was, or actually division, dividing it out, came out to 803.1 psi. That is rounded to the nearest 5 psi for a final value of 805. Now, in the event that your fracture occurs in the area of 5% outside the middle third of the span length, then you'd use case 2 to do the calculations. A being the distance from the fracture to the nearest load supporting block, which would be, of course, the blocks that are underneath. And that situation actually is fairly rare. So we didn't highlight it here, but should you come across it, refer to your textbook, and it has an excellent explanation on how to measure that A value and to come up with your modulus of rupture value. The third case, of course, is if the fracture is outside of that 5% range, in which case you simply discard the sample and the results are of no value. So that's it. Well, we hope your beams test in Flexure and pass and give you great incentive money in the future. So this concludes this video.